patrol vehicle operates as a highly active, heavily targeted data endpoint moving through public space. It represents the most exposed node on any law enforcement network. Looking at this technical schematic, we see the focal point, the mobile data terminal. Pushing access to sensitive databases into a moving car creates a severe structural paradox. We are placing critical infrastructure inside a chaotic environment, introducing hidden deployment complexities. This comparison table outlines the environmental survival imperative. Standard consumer hardware fails rapidly here. A rugged MDT must withstand oven-like thermal loads inside a parked cruiser, sitting in direct sunlight, while simultaneously absorbing the kinetic stress of constant driving vibrations. This diagram shows the physical cabin constraints. Bulky, ruggedized units must be securely anchored within crowded center consoles, without blocking essential operational controls. Furthermore, loosely mounted laptops transform into deadly projectiles during a high-speed crash or airbag deployment. Physical survivability ensures the hardware remains operational, but the digital integrity of the data requires an entirely different set of architectural defenses. The information actively displaying on an MDT includes nationwide criminal histories from the NCIC, live arrest warrants, and sensitive dispatch locations. This diagram illustrates the zero-trust architecture required to defend that information. The outermost threat layer begins with the physical vehicle, a prime target for physical theft. To prevent breaches, hardware and software must maintain strict alignment with federal CGIS mandates. A rugged hardware suite lacking this zero-trust foundation leaves the patrol fleet functioning as a distributed, unsecured entry point into the department's core servers. Securing the network requires robust software, and running that software requires significant processing power. Standard enterprise IT specifications are entirely insufficient for the field. This load graphic breaks down the processing burden. Officers continuously use resource-heavy computer-aided dispatch, or CAD. Executing these programs pushes CPU performance toward maximum capacity. Alongside CAD, they run records management systems, whose complex legacy code drastically increases RAM utilization well beyond normal baselines. This integration friction chart shows the disconnect that often happens during procurement. Suppliers of rugged field tech frequently struggle to harmonize their proprietary hardware with a precinct's existing back-end servers, generating massive administrative friction for IT staff. This shift timeline graph reveals the idling power challenge. MDTs must execute heavy software loads without draining the cruiser's primary battery. Generic adapters cause the steep depletion seen here. Maintaining continuity requires dedicated subsystems that output a flat, reliable voltage curve across the shift. Without massive processing headroom and stable power delivery, the software gridlocks. A single power failure in the field results in an instant, total loss of dispatch communication during critical incidents. Processing power and battery life mean nothing if the MDT cannot communicate with the precinct. Uninterrupted connectivity is the backbone of the entire deployment. Law enforcement vehicles rely on specialized physical hardware, like cellular air cards and dedicated mobile routers, to bridge the connectivity gap to the open airwaves. Geographic realities dictate that patrol operations will constantly pass through cellular dead zones. Standard network configurations cause data feeds to buffer and drop out completely. This secure connectivity topology outlines how the network survives. The cellular backbone transmits data from the isolated MDT toward the wider network. From there, all data routes through hardened, encrypted VPN tunnels, securely penetrating the precinct's internal firewalls from the open airwaves. These encrypted tunnels are strictly non-negotiable. They provide the only secure method for an officer to execute real-time handshakes with databases to run license plates and retrieve criminal histories. Even with encrypted tunnels and rugged mounts, we have to account for the scenario where physical vehicle security fails and an active, powered-on MDT falls into unauthorized hands. Standard alphanumeric password policies fail in the field. Officers reacting to high-stress, kinetic situations cannot be expected to reliably type complex security codes to access dispatch instructions. Returning to the zero-trust architecture diagram, we see the solution in the center layer. Access requires frictionless authentication, a system that balances extreme, instantaneous security with operational speed. Integrated biometric login interfaces serve as the primary method to lock down the device. A fingerprint scan allows immediate entry without causing dangerous operational delays. Biometric authentication separates the physical machine from the digital access it provides. Stealing the hardware no longer grants access to the federal data layer. Digital networks and biometric hardware still rely on human operators. The most hardened IT architecture will collapse if the officers actively circumvent it or reject the system entirely. This adoption matrix maps the human barrier. Deployments face a trust deficit and veteran resistance as officers struggle with unfamiliar digital workflows. Distributing technical manuals strands users in a low-trust failure state. Departments must execute hands-on, scenario-based training to build trust and operationalize their investment. Physical training is a requirement, not an administrative afterthought. It is a critical cybersecurity vulnerability patch designed specifically for the human element. This deployment economics graphic illustrates the true financial scope. Budgeting solely for the rugged PC ignores the massive infrastructure below the waterline. A functional MDT deployment demands a holistic suite, including custom mounts, cellular modems, power relays, and specialized software licenses. This strategic deployment phasing diagram details how to roll out that suite. Departments must map their IT infrastructure and pilot the hardware in a single vehicle to expose power draw flaws and mounting hazards prior to any broader fleet acquisition. Finally, this deployment synthesis matrix visualizes what true mission readiness looks like by bringing all three critical vectors together. Field deployment only succeeds when environmental survival, strict IT system integration, and the officer's ergonomic and operational experience perfectly overlap. Engineering a rugged laptop is straightforward. Mastering the complete, secure mobile ecosystem is the only way to protect the officers on the road, secure vital criminal data, and guarantee an uninterrupted emergency response.